Okay, I'm just going to go over the final project first rough draft submission and 50% code submission. So the final project, well, is going to be going over infrared and RGB images. And so we are looking at the code here first. Um, so we're loading our data set into our generators, our training data set generator and our validation data set generator. Um, One thing that's interesting about these generators is that they are not consumed by just, they can be used indefinitely. Okay, so we're going to train the models in this method here. Let's see. I added an early stopping condition, and so that if there's no improvement after seven epochs, then it'll terminate the epochs and end early and not waste a bunch of time with non-improvement. And then if there after 3 epochs, if there's no improvement, then it'll reduce the learning rate. And that ended up being really beneficial. So that impacted getting some of those like squeezing out like another couple percentage points in accuracy for a number of the top models. So that proved to be a worthwhile addition. Okay, and then I added my own score, which is not very high tech, and there's a much better way to do it. But I just did it this way for ease, and I might change it down the road, but probably not because I've already run a lot of trials. So, okay. But I'm just trying to combine the validation accuracy, the average validation accuracy, the average gap, which is kind of a measure of overfitting, the average best accuracy. Since this is a competition, I weighted that heavier so that it looked for the ultimate best accuracy. And one thing about this early stopping condition is that it rolls it back to the best weights, which is really handy and also makes this best accuracy something that is a worthwhile addition to the scoring when it comes to the competition. Then also adding in average validation loss. So I kind of tried to take those things and combine them into a single score to identify the top models that I could then go forward from and apply the additional metrics to, which are going to be the, previously we've been looking just at pretty much validation accuracy. But for this project, we want to look at some more complicated measures of fitness for the models. So we're adding in F1 score, the area under the curve, the confusion matrix, and then my KL score. Okay. So this is just sort of the preliminary hyperparameter tuning score to try to determine which direction to head in terms of hyperparameters. And then later on, we're going to take those top models and then we're going to apply the new metrics to them. Okay, and then when saving the file, there's some conversion that needs to happen. This is the very overly complicated save file method. Probably didn't need to be that much, but I really wanted to make sure. It gets a little complicated when you go to sleep and wake up, and it's nice to just see all these printouts that tell you that everything went okay. So then loading the models back up, and then we are plotting the accuracy, plotting the loss. And then I noticed that the files that were included in that were the let's see here. The annotated COCO annotation counts. I guess this was taken from a larger data set because these numbers are not correct for what's in here. So anyway, I recalculated those to get my own counts for the data so that I could understand the distribution and how balanced the data set was ahead of time. And then if there are any issues that come up, I might look at rebalancing, taking efforts to rebalance the data. I haven't yet done that in any of the projects, and so it would be a fun opportunity to kind of learn strategies on doing that. But my results actually indicate, I mean, so far my results have been really good. So I've made some adjustments to the basic architecture, and that really seemed to help. I think I just sort of glossed over some of the important aspects in previous projects in terms of the number of hidden units in the layers and sort of making it more complicated in terms of building that, because I like to build them so that I don't have to just rewrite it every time. So I reworked that so that it can sort of auto build the right degradation. What am I trying to say? The right number of units. Let me just get over to here so I can say it correctly. Okay. Build scratch. Okay. So we start with the number of layers, and we start with the number of filters. And so if, based on the number of filters, we start with, based on the number of layers, we start with this number of filters, and then we increase it by a power of 2 based on the number of layers for the CNN layers. And then when we get to the DNN layers, we bump it up a notch but max it out at 1024, because if it went to 2048, that was when my computer was like, nope, I'm not going to be able to handle that. But max pooling, of course, helps with that quite a bit. So I added in some max pooling layers so that I could push this a little bit further, and because it was like 512, and then I got it up to 1024. And so after it gets to 1024 for the first DNN layer for the hidden units, then it starts going down by powers of 2 until it reaches the final classifier. So in previous models, I sort of glossed over that and just had a really basic, all the layers ended up having the same number of filters, and then the DNN layers was just sort of, I did it backwards, actually. I think I divided by 2 with the starting DNN layer instead of multiplying by 2 by the starting DNN layer, which it's better, from what I've read, it's better to go up here than down in the number of units when it's taking in the CNN layer. So anyway, made that a little bit more correct or the way people normally do it. And that, I don't know if it was that or, I mean, I changed so many things. It's hard to know, but my scores are much improved from my previous models. So I was happy about that. Okay, so then we're creating our parameter list. Oh gosh, I'm going over on time. So let me just get to the future of the project. So I've got all the results. So here's my experiment 1 is hyperparameter tuning. So it's just finding all the best models and the hyperparameters that work the best. And then experiment 2, and so I've done the CNN Scratch and I've done the CNN VGG16, but I have not done yet the autoencoder plus network pipeline. So these are just placeholders. This is not the data that goes in here, but the data in the previous 2 is correct and the accurate data. But this one is not complete yet. These are just dummy placeholders. And then, so the experiment 1 is the hyperparameter tuning. Experiment 2 is identifying misclassified images. So I want to kind of, I might change this or come up with more, or maybe this is too much, but basically I want to look at images that are misclassified across all the top models for all architectures. The same image is misclassified. Then the same image is misclassified across all top models of one architecture, but not across all top models of another architecture. Then an image that is the same wrong class. So not only is it the same image that's been misclassified, but all the top models have also misclassified it with the same wrong class. I don't know if that has happened, but I want to see if it has. And then all different classes. So everybody's confused. Nobody even knows what it is. So every model, every top model has a different class for the same image. It's the same image, but all different classes. And then 5 is a review of the minority class misclassifications. Is that, so going back to that class imbalance, is that an issue, or are most of the misclassifications happening in the dominant classes anyways? Okay, and then experiment 3 is going to be to cross-examine all performance metrics listed, above, for each of the top models of each architecture. Okay, and then determine the best one. Okay, thank you very much.